Robot Talk is the podcast that sits down with robot enthusiasts from around the world and asks them the questions you always wanted answered. Like, how does that robot know where it's going? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and I'm so excited to be back for a new season. I'm feeling refreshed after my summer break, and I'm ready to talk robots. I've got lots of fascinating guests lined up for you over the coming weeks and months, covering all different areas of robotics. This week, I'm finding out how robots work out where they are and navigate through different environments, from the seafloor to the racing track. But first, I'm thrilled to tell you about the new Robot Talk community on Patreon, which I launched over the summer. If you don't know about Patreon, it's a platform where creative people can share their work and where their fans can support them to keep creating new, awesome stuff. My aim on Patreon is to interact more with you, the listeners, to create a welcoming and inclusive community where we can chat about robots and about the podcast, and to ensure the long-term sustainability of the podcast through generous donations from people like you. So please check it out by going to patreon.com/Claire Asher. And if you can, consider supporting the podcast for just £5 a month. The first 20 Patreon supporters get a free Robot Talk sticker. And a quick shout out to my new Patreon supporter, Jonathan Walker. I can't thank you enough for supporting the podcast. Welcome to the Robot Talk community. So, with all that said, I'm excited to introduce this week's guest. I recently had a really interesting chat with John Leonard from Massachusetts Institute of Technology about autonomous navigation for underwater vehicles and self-driving cars. This week, I'm talking to John Leonard, a professor of mechanical and ocean engineering at Massachusetts Institute of Technology, working on navigation and mapping for autonomous mobile robots. Hi, John. Great to have you on Robot Talk.
Hi, Claire. My pleasure.
So your research is focused on helping robots to navigate and understand the world around them. So to get us started, what makes this task challenging and what is the kind of current state of the art?
Great. Yeah. I've been obsessed with the problem of how we can enable robots to navigate my whole career. I started as a PhD student in Oxford in the UK in 1987. And it's been, I think, 37 years since then. Yeah. And I'm still working on my PhD thesis. I tell people I've just been obsessed with this problem because as robots move in the world, there's uncertainty in their measurements of their motion. And when they take observations of the world, then they have uncertainty in the sensor readings for, like, say, detecting objects, detecting places. And so the question of how a robot can sort of pull itself up by its own bootstraps of sort of starting to move around the world, building a representation of the world, while concurrently using that to locate themselves. We call that localization. And then ultimately use that for route choice, path planning, navigation. And so this problem of how robots navigate and build maps has kind of been a central research question in mobile robotics. It's challenging because it turns into a very high-dimensional state estimation problem with lots of uncertainty and interesting questions about representation. It's also really critical for applications. So say a planetary rover on another planet or a self-driving car, an underwater robot, a space robot, in lots of different settings, the question of how to locate the robot or platform while it's kind of moving and collecting data for its mission is just a really central question.
Yeah. So the alternative option, which I guess would be used in a really well-known environment, would be just to give it a map and say, you know, this is what the environment you're in is, which is no good if you want to do any kind of exploration or anything in an environment that might change or be unknown.
Correct. Yeah. So a lot of times, say in a factory, they might put beacons, like little fiducial markers or ultra-wideband radar transmitters in the environment. Underwater, we might deploy acoustic transponders in a limited area. or outdoors, robots can use GPS to measure their position quite accurately, as long as they're not, say, in an urban canyon, like near tall buildings.
Right.
But for this exploring the unknown, and robots that are kind of lifelong autonomous, self-learning systems that sort of go out and get data about the world and then update the representations, that kind of feeling is that the questions involved in this navigation problem, they're kind of building blocks towards the kind of more robust autonomous behavior in the world.
Yeah, what I love about so many of these problems in robotics is that we're trying to do what evolution has already solved with animals, right? And we do these things without thinking about them. But translating that into a robot is really quite difficult.
There are some amazing inspirations from nature, like the long distance navigation of migrating birds, and the navigation of humpback whales and other marine critters.
Yeah.
So somehow, through evolution, the sort of ability to explore and find your way home is just critical. And despite all the sort of advances in AI, ChatGPT, the sort of self-driving cars we see in the news, like Waymo and Tesla Autopilot, there's still some really fundamental unanswered questions, I think, about how we could come anywhere close to natural animal systems in the ability to navigate.
Yeah. And so coming back to what this current state of the art is, can you kind of explain, like, what can autonomous mobile robots do now and what are they still struggling with?
Great question. So I think that there's been a lot of progress in the last few decades with an approach that we call pose graph optimization.
Okay.
If we think of the robot traveling through a sequence of locations where we have the pose of the robot, the position and orientation. And a lot of it comes down to the question of how do you represent the trajectory of the robot and the environment. And the field over the last few decades settled on these pose graph optimization algorithms. It's kind of like Hansel and Gretel, where you're leaving behind a virtual breadcrumb as the robot moves through the world, and then posing an optimization problem to find sort of the optimal arrangement of the breadcrumbs to best match the data to make it as consistent as possible. Okay. So, for example, one of the subproblems we call loop closing. Have you ever had the experience, perhaps in a foreign city, maybe you're in Paris and you take the metro and you get off one station, you go walk a long way, you get on the metro again, you come out through another station, you walk a long way, you get back to somewhere you've been before, like Notre Dame. We call that loop closing, is what happens when you take a sort of potentially circuitous route around the world and come back to where you started. And for a robot, when it comes back to a place it's been before, what it can do is it can use that as a constraint. So the sort of trail of breadcrumbs that was left behind as the robot was traveling, if it comes back and says, oh, I'm back at the Eiffel Tower, it can apply a correction to find the optimal fit of the trajectory it just took. Yeah. So as robots perform this process we call SLAM, simultaneous localization and mapping, it's doing a whole sequence of either little or big loop closing kind of events to sort of make the representation of the world consistent while figuring out, is it in a place it's been before or a new place?
And how does it know for sure that it's back in a place it's been before? I mean, if you have something like the Eiffel Tower, it's quite easy, but in less distinctive environments.
That's a great question. So what can happen is called perceptual aliasing, where you might have a building. For example, at MIT, we have this large interconnected set of corridors, and obviously there are things like room numbers that are unique identifiers, but just looking at a corridor, or say you're in an airport and you have all the gate numbers and so forth, but just looking at the geometry and the appearance, it's actually quite easy to have situations where multiple places might look the same. And so it's an instance of what we call the data association problem, which is how you tell which measurements correspond to which kind of elements in your map. And it's a sort of exponentially complex problem, like as you go through all the permutations of the different options. And so this kind of perceptual aliasing problem is one of the reasons why things are difficult. And I'll just say one more thing is, what happens to a robot is if it makes a mistake. I'm trying to think from my world travels as a roboticist. I've been all over the globe. But, situations, for example, in London, or where I was kind of confused, and I thought I was in a certain place, but it was actually the wrong place. When robots make mistakes with this kind of loop closing or data association, a challenge with current algorithms, even today in 2024, is that mistakes can cause the entire map to be corrupted, and it can kind of like fall apart. So a lot of times everything's great if you sort of fingers crossed, no big mistakes. But when mistakes happen, they can be catastrophic. And that's the kind of robustness challenge that we're working on.
Yeah. So one area that you're applying this to is underwater robots. And we've talked a little bit on the podcast before about how this environment is even more challenging than some terrestrial environments for reasons like poor visibility and communication issues underwater. So how are you designing robots that can kind of navigate effectively in underwater environments?
Yeah, underwater is difficult because we don't have GPS. GPS doesn't work underwater. And typically the water visibility is very poor, as you mentioned. And without the ability to transmit electromagnetic waves, we rely on acoustic modem technology. If you think about the old sort of dial-up modems of the 1980s with the kind of dial-up sounds, that's kind of, even that level of bandwidth is too much or optimistic for what we have underwater. Okay. For example, for a scientific mission, biologists might like to survey a coral reef and try to take very detailed kind of pictures and stitch them all together to make a kind of map, maybe come back 6 months later and say, has the coral reef, has its health deteriorated or improved or kind of the same? And to accomplish a mission like that, one approach is this mapping and localization problem where you don't want to have to deploy transponders or fiducial markers. You want to kind of use the coral reef as you're mapping it, as a person might, to try to ensure the consistency. So for underwater SLAM, a lot of the same challenges are there, like this kind of breadcrumb trail pose graph optimization problem, the place recognition, data association, perceptual aliasing. But we're doing it with sensors that are more difficult. For example, sonar, sound navigation and ranging, is an important modality underwater. Sonar images can see further than optical images underwater using sound waves, but they can be very challenging to interpret. You mentioned earlier sort of the inspiration from biology. I've had a long inspiration from dolphins, and their underwater sonars are really remarkable at their ability to detect, for example, buried objects. And we're still like have barely scratched the surface in terms of systems that kind of mimic underwater sonar systems. But what we do have, for example, led by the commercial offshore industry, are some very high resolution sonar devices that create these acoustic pictures underwater. And one of the projects I've been involved, for example, over the last 10 years has been using underwater sonar cameras, in effect, to try to make mosaics or kind of stitch together multiple images of, say, the hull of a ship to do inspection, and or to, say, do a coral reef. I have a colleague, formerly from Woods Hole Oceanographic Institution, Hanu Singh, now at Northeastern, who had some quite beautiful, amazing results using cameras to stitch together a bunch of images to map an ancient shipwreck underwater.
Oh, cool.
Or even to map the Titanic. And so underwater, it's a lot of the same problem formulation and structure as for any other kind of robot, but with some unique sensing challenges.
And so, I mean, you mentioned dolphins, and I know that one issue for a lot of marine life is that the ocean is a lot noisier than it was, a few hundred years ago before we kind of humans charged in and started making all kinds of noise. Do you run into the same kind of problems using sonar for robots, that there's interference from other man-made sources of noise?
Yeah, I've been fortunate over my MIT career now this is the beginning of my 29th year as a faculty member, which I can't believe. But over the years, I've had a lot of collaborations with the Woods Hole Oceanographic Institution, we call it WHOI. And I've been on the PhD committees of biologists that have looked at the acoustic system, for example, of whales and dolphins. And so I have to confess that I am not an expert. Like, I have very limited knowledge. But what I've seen through these collaborations is that, for example, in the US and worldwide, researchers have to be, and I support being very careful about how you use acoustics in research if there might be sort of whales or dolphins nearby. But in general, for robots, they tend to use much higher frequency sonar systems.
Okay.
And one of the things that makes sound an interesting kind of and challenging problem underwater is for high resolution. So to get really detailed pictures, we'd like to use a very, very high frequency.
Yeah.
Say if the speed of sound in water is about 1,500 meters per second, you can do the math and figure out, okay, with a high frequency sonar, what would it take for the frequency for having a wavelength of 1 centimeter or 1 millimeter? And when you go to those higher frequencies, for example, say for a millimeter up to 1.5 megahertz, the reality underwater is that the attenuation of sound waves, the attenuation gets stronger and stronger very dramatically at very high frequencies. So most robots use very comparatively high frequency sonars to try to get good pictures, but the sound dies off very quickly. In contrast, like say humpback whales use very low frequency sounds that can travel very long ranges to, for example, communicate with one another at hundreds of kilometers apart. So in my experience, nearly everything is high frequency. And so even though we need to be careful, for example, we did experiments with NATO 15, 20 years ago, if there was any sighting of any marine mammal anywhere in the vicinity, all operations would cease, things like that. But most of what we do is outside of the range that biologists would be concerned with.
Good. Well, I was watching your TED Talk, and you also mentioned it at the beginning of this conversation about designing long-lived robots that can build and maintain models of the world through lifelong learning. How might a system like that work?
I was thinking about this again on the subway coming in this morning. I think what we need are robots that can learn from their experience. For example, if I had a tabletop with some objects on it, and if I could move a few of the objects, like say I move my cup, I move my phone, a child would have the ability to know what changed in the environment and move the objects back to where they started. In robotics, I call this the undo for the physical world problem. It's like Sesame Street. Which one of these things is different? That kind of, there's very elementary questions about what has happened in the world over time. And to date, there's not been a lot of work in that area in robotics. If you look at the large language models and the vision language models, such as ChatGPT, that are sort of taking the world by storm, and earlier the sort of pre-trained image models like ImageNet and Facebook have something called Segment Anything, where they trained it on 1 billion images.
Wow.
These large models have vast amounts of data harvested from the whole internet, and it gives them very amazing performance, for example, identifying a cup versus a water bottle. But what robots don't have is the ability to learn from a very small number of examples and to learn from their own experience. And so a lifelong learning autonomous robot, it might have one of those large models as a kind of foundation. It's one of the words they call them, foundation models, which it's hard to argue against using them because they're so good. But imagine a robot that you turned it on, and for a few hours each day, it kind of navigated around a small part of the world and interacted with the world, moving some objects, maybe with a human teacher, kind of moving some objects, maybe. And then the robot went to sleep. It charged its batteries overnight. But while it's asleep, it's dreaming. It's processing the data that it took during its waking hours. And it was kind of like compressing and distilling its representations in such a way that the next day when it wakes up, it's better able to do tasks in the world. It recognizes the cup and the water bottle immediately from its own experience, or it can put objects back in the place they were the day before when they went to, quote, sleep. And so I call this robot dreaming. Like if you had robots that could kind of gradually over time make better sense of the world from their own experiences. The hard thing about intelligence is not what to remember or remembering everything. We're at the point where you can kind of remember everything, but what you need is the ability to rapidly recall the pertinent information in a given moment. And so I think the hard part is knowing what to forget.
Yeah. So
we know now how to train a segmentation model with 1 billion input images, but children learning at home with some play or in the daycare, they're not getting 1 billion images from around the internet. They're interacting in a very small scale way And there's, I think, the tactile kind of touch and motion and dynamics aspect. It's not enough just to look. I think we have to look and touch and interact. That sort of, we call that embodied intelligence. And so how do you create a system that knows what to forget and what to remember in a more efficient, compact representation, that it's like, bam, it can quickly get the answer and know that it got the answer.
Yeah, that's fascinating. I love the idea of robot dreaming. We don't fully understand why we dream, but what you've just described is pretty much the best guess we have.
That's what I think. And I have no sort of scientific basis to say that, but I think dreaming is reprocessing whatever is in it to make us better for the next day.
Definitely, yeah. And so what kind of applications do you think this sort of lifelong learning robot might be used for?
So imagine a home companion for an elderly person. So my father's 87 and 3/4 years old and somehow living mostly on his own. And if I could have a robot that could truly help him with tasks, the market potential is enormous with the aging society worldwide. But the challenges to deploying robots in the home are just monumental. Mistakes are unforgivable. You need, so kind of the robots to help people is kind of my goal. And I think other applications might be, robots in factories, all the applications that have been in your podcast series, agriculture. But my dream is not to replace human workers or to put people kind of out of work or out of roles. My goal is to sort of complement humans, keep people in charge, and find robots that can basically give people superpowers, like the ability to lift heavy objects or the ability to do things they used to be able to do when they were 25 and now they're 85. And for that, you could almost imagine like a lifelong learning robot that could custom tailor their learning to a particular person, to sort of help with what they need, for example.
Yeah, amazing. Yeah, that would be fantastic. So earlier we touched briefly on the idea of kind of self-driving vehicles, and you are also technical advisor at Toyota Research Institute, where you research human interactive driving and human-centric AI technologies. So can you tell me a bit about the work that you're doing there?
Yeah. So I got involved in self-driving as an MIT professor with some wonderful colleagues in something called the DARPA Urban Challenge in 2007. It was a robotic car race that had Stanford and Carnegie Mellon and a whole bunch of other folks. And the goal was to develop a robot that could drive autonomously for 60 miles in traffic with other robots. And it was part of this, there was a 3-part DARPA challenge series that's kind of viewed 20 years hence as part of like the formative kind of boost for self-driving technology. And in fact, after the DARPA Urban Challenge, Google hired some of the leaders from Carnegie Mellon and Stanford to create their self-driving car project, which is now called Waymo, which has been phenomenally successful. I think they're now doing 100,000 trips a week, some very amazing number of rides and vehicles. And so, but I was asked to join Toyota in 2016 to help create this new entity called Toyota Research Institute. And TRI aims to be the sort of long-range, high-risk, high-reward research arm of Toyota. And in TRI, I was earlier involved in some self-driving related efforts. And as the industry evolved, and there's a lot of, Waymo are clearly the leading front runner in the sort of robotaxi space. But if you look at companies like Tesla and Mobileye and Wave and Cruise, there's a large number of folks pursuing this sort of fully autonomous automated driving, and Toyota indeed has efforts to do that as part of its other entities. But in TRI, we want to sort of work on things that are like beyond the horizon, like what does the future sort of 10 to 15 years look like? And so the notion of human interactive driving, where, to be honest, I'm just an advisor now. Our human interactive team is led by a wonderful man named Avinash Balachandran, who's a Stanford grad. And it's a small team, but its sort of central hypothesis is that, well, yes, robotaxis are coming and there'll be highly automated driving systems. But the central hypothesis is that for many people, they will still want to drive. We will have humans driving cars for a very long time. And can we, instead of replacing the human, let's say a robotaxi, can we augment the human with AI? And so how can we take the skills of expert race drivers or highly trained, careful drivers and find a way to have a kind of a blend of the human and the robot kind of capabilities? For example, for teenage drivers, to help them be better drivers through better safety systems, and there are kind of ADAS assist systems coming. But beyond just, say, emergency braking, lane keep assist, could you imagine a robotic teacher? We call this sometimes the driving sensei, that could help make you a better driver and help give you skills that make you a better driver for life, or help an elderly driver to keep their skills. And so what's involved is trying to find ways where we can use some of the advances in AI to combine that with models of human performance. How do people drive? How do people react to technology? And try to get a blend of the best of the human and the AI system with a sort of 1 + 1 = 3, not, but more than the sum of its parts.
Yeah, amazing. So one project I'm aware of that Toyota Research Institute have been working on is autonomous drifting. So could you talk a little bit about that?
Sure. We have a number of projects, for example, related to driving, teaching, in effect, sort of amplifying like human driving for normal, ordinary drivers. But we also have a focused effort in high performance driving in sort of two strands. One is for racing and one is for drifting. And drift driving is an extremely challenging task where highly trained humans can operate the car outside of its normal performance envelope. So normally your car can tolerate a certain amount of side slip and a certain amount of yaw rate. And if you go out of that kind of window and in the phase space, you're probably going to go off the road, But highly skilled drift drivers have developed ways to take the car beyond its kind of design envelope and do very precise maneuvering. And we've used the drift racing as a challenge problem to use this kind of human interactive AI approach. So we've done some highly challenging drift demonstrations on a test track in California, for example, and a few other places where we've done automated drifting. And the team recently released a video on tandem drifting, two cars drifting together.
Okay.
And so drifting is kind of we look to the extremes. It's a bit like the ocean when you try to work in the ocean. And by the way, I don't do a lot of work in the deep ocean. Folks at Woods Hole are very good at that. But when you go to the extremes, you go to the deep ocean, it really forces your assumptions. In a similar way, drift driving and racing, when you go to the extremes, it forces you to question your assumptions. And our hypothesis is that advances there over time can percolate into the larger fleet of vehicles, millions of vehicles a year. So that, for example, if a teenager was skidding on a sheet of ice and the car was starting to lose control, that maybe some of the drift thinking technology could basically come into play to get back into control. Yeah. That's our vision.
Yeah, I watched the drifting video. I didn't see the tandem drifting. I'm going to have to go and try and find that one now. But it's really, really impressive.
Thank you.
I think because obviously there's a race driver sat there, I guess, just in case, not doing anything. That must be quite a surreal experience.
Right. Well, we have quite an amazing team. It's a small team, but I want to minimize my direct impact on that particular demo because I've partly just helped to set some of the strategic goals, but Avinash, a few other folks, just really, really deeply obsessed and immersed with this high performance driving. And I do think that small teams can sometimes outperform big teams in the sense that just the right small number of really highly focused folks can do some really cool things.
Yeah, absolutely. Well, your research is fascinating. We'll continue to watch what you get up to with interest. John, it's been fascinating chatting to you today. I've been speaking to John Leonard from Massachusetts Institute of Technology. Thanks, John.
Thank you very much.
Thanks for listening. If you enjoy Robot Talk, please share the podcast, subscribe, and leave a review. It really helps boost the podcast, so thanks in advance. And if you've got a question you'd like me to ask one of my future guests, you can contact me on social media at Robot Talk Pod, on Patreon at patreon.com/Claire Asher or at robottalk.org. I regularly announce upcoming guests on all those platforms, and I'd love to include your questions in my next interview. Next week, I'm talking to Gisela Reyes-Cruz from the University of Nottingham about human-robot interaction. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk is brought to you by the Hamlin Centre, Imperial College London.